All right, let's try this again. See if I can stop the screensaver. You should be able to see my screen now. Is that good? You seeing me again?
Yes, sir.
All right. Sorry about that. Screensaver shut the program down completely. That happens. So what I was saying is that the type of the alcohol product that you're forming depends on the identity of both the carbonyl group and the reactant. Right? So if you start with an aldehyde, you can get a primary alcohol with a hydride reducing agent, or you can get a secondary alcohol with an organometallic. Right? Because here you're making a new CC bond, and here you're not. Right? The aldehyde already has one hydrogen attached to it. This would provide a second hydrogen to make the primary alcohol. This would provide a second carbon-carbon bond to generate the secondary alcohol. If you start with a ketone, then you'll get a secondary alcohol with the hydride reducing agent, and you'll get a tertiary alcohol with an organometallic. Right? Because again, you're making a new CC bond with the organometallic. The ketone doesn't have any hydrogen attached to the carbonyl to begin with, but if you add a hydride source, you'll produce that, you'll add that one hydrogen, which will make the secondary alcohol. If you make a new CC bond, then you've got 3 CC bonds. And if you start with formaldehyde, which already has 2 hydrogens attached to the carbonyl, then you'll make a primary alcohol with an organometallic reagent. And obviously, if you used a hydride reducing agent, you'd make methanol. So that's not a very interesting reaction. So there's a large number of possible combinations of reducing agent and carbonyl compound that will generate different types of alcohol. But it doesn't really matter. Any aldehyde gives a primary alcohol with either of the hydride sources and a secondary alcohol with either of the organometallics. Right? Ketones, secondary alcohol, doesn't matter which hydride source you use. Either of them is going to yield the secondary alcohol. Any of the organometallic reagents give the tertiary alcohol. So when you're making your note cards, you could make a really large number of note cards because of all the different possibilities. But really, you just kind of have to see the overarching theme of what type of atom you're adding, whether you're adding another hydrogen or not, and how many hydrogens you start out with, right? So you see how many hydrogens there are in the molecule. Formaldehyde has 2 hydrogens already attached to the carbonyl. Aldehydes have 1 hydrogen. Ketones have none. And then you decide if you're adding additional hydrogens, and that will tell you whether it's primary, secondary, or tertiary alcohol. Questions? Comments? All right, so the other thing that's in Chapter 8 is oxidation reactions, which are the reverse of the hydride reduction. These take alcohols to make carbonyl compounds. By removing 2 hydrogens. So obviously it doesn't work on a tertiary alcohol. Since the carbon has no hydrogen. But it will work on secondary alcohols and primary alcohols. Secondary alcohols we use ketones. And because the secondary alcohol has one hydrogen attached, which means when you remove the two hydrogens, it will no longer have any hydrogens attached. And aldehydes will come from primary alcohols. Right, because the primary alcohol has two hydrogens attached already. When you remove hydrogen, this one stays attached. So it goes from two hydrogens to one hydrogen attached. There is a small catch, though, which is that in aqueous acid, the aldehyde gets oxidized. To the carboxylic acid. So that initial aldehyde product, RCOH, in the presence of an oxidizing agent like potassium dichromate in aqueous acid, right? This is the key. If the aqueous acid is present, then you can't stop the aldehyde from getting further oxidized by inserting an oxygen in between the carbon-oxygen bond to get a carboxylic acid. That is usually not what we want. We call it overoxidation. And to solve the problem, we have to do it not in aqueous acid, because we can't stop the aldehyde in aqueous acid from forming what's called a hydrate. And that forms reversibly. Once you have that hydrate, you can remove hydrogen again to get the carboxylic acid, so you remove a second set of hydrogens. So this is an equilibrium, but as soon as you form this, you're going to oxidize that up to the carboxylic acid. So there's a bunch of different reactions in chapter 8, but there aren't a bunch of different classes of reaction. Right? Most of them are nucleophilic acyl addition reactions. These oxidation reactions are a nucleophilic acyl substitution, followed by an E2 elimination. So we're introducing two different types of reaction, nucleophilic acyl addition and nucleophilic acyl substitution. So that's what I have to kind of as a summary of chapter 8. So basically what I'm going to do is I'm going to give you some oxidation reactions, some reduction reactions, some organometallic reactions, and ask you to figure out what the nucleophile is. Is it a carbon minus or a hydrogen minus? And based on what kind of carbonyl, are you making a primary or secondary alcohol, or for oxidation, are you going backwards, right? So are you taking a primary alcohol to an aldehyde, or are you taking a secondary alcohol? And of course, if you see a tertiary alcohol, right, tertiary alcohols, because they have no hydrogen, you can't actually oxidize. You can do the nucleophilic acyl substitution, but the E2 elimination is only possible if there's a hydrogen on the carbon that bears the alcohol.